Good morning. This presentation examines how climate data can support informed decision-making on land use and infrastructure within disaster risk reduction. The core argument is that climate data should not remain only as scientific information, it should be translated into planning, investment and governance decisions. As climate change intensifies extreme weather, public institutions need more reliable ways to anticipate risk rather than respond only after damage occurs. I will explain why climate data matters, which tools and data sources are most relevant, how this information can support planning and crisis management, what barriers still limit implementation, and which framework can help move from data to action. Overall, the presentation proposes a practical bridge between climate knowledge and disaster-resilient decision-making. The starting point of this discussion is the growing pressure created by climate change. Rising temperatures, irregular precipitation, heat waves, floods and storms are increasing systemic risk across settlements and infrastructure networks. In this context, decision-making can no longer rely only on past averages or isolated observations. It requires robust, validated and multi-source climate datasets that allow planners and decision-makers to understand both current conditions and future trends. The objective of this presentation is to introduce a structured framework for integrating climate data into land use planning and infrastructure decisions in line with disaster risk reduction principles. The starting point of this discussion is the growing pressure created by climate change. Rising temperatures, irregular precipitation, heat waves, floods and storms are increasing systemic risk across settlements and infrastructure networks. In this context, decision-making can no longer rely only on past averages or isolated observations. It requires robust, validated and multi-source climate datasets that allow planners and decision-makers to understand both current conditions and future trends. The objective of this presentation is to introduce a structured framework for integrating climate data into land use planning and infrastructure decisions in line with disaster risk reduction principles. The starting point of this discussion is the growing pressure created by climate change. Rising temperatures, irregular precipitation, heat waves, floods and storms are increasing systemic risk across settlements and infrastructure networks. In this context, decision-making can no longer rely only on past averages or isolated observations. It requires robust, validated and multi-source climate datasets that allow planners and decision-makers to understand both current conditions and future trends. The objective of this presentation is to introduce a structured framework for integrating climate data into land use planning and infrastructure decisions in line with disaster risk reduction principles. This means treating climate data as an operational input for governance, not as background information. The emphasis is on evidence-based planning, anticipatory action and long-term resilience. By using climate information systematically, institutions can reduce uncertainty, improve preparedness and make development choices that are safer, more adaptive and more sustainable over time. Climate data matters because it shifts governance from reaction to prevention. Instead of waiting for floods, droughts or heat events to create losses, institutions can identify exposure, vulnerability and hazard patterns in advance. This improves risk assessments and helps planners understand where development should be limited, adapted or protected. Climate data also supports infrastructure planning across the full life cycle, from design to maintenance and upgrading. Because future climate conditions may differ from historical patterns, roads, drainage systems, energy networks and public spaces must be designed for uncertainty. Another important aspect is policy alignment. Climate-informed decisions connect local planning with international frameworks such as the Sendai Framework, the Sustainable Development Goals and the Paris Agreement. Climate data is therefore not only technical evidence. It is also a strategic resource that helps governments justify decisions, prioritize investments and strengthen resilience in a transparent and accountable way. Several international examples show that climate data can be effectively integrated into decision-making when supported by the right institutions and tools. In the Netherlands, the Deltares and Climate Adaptation Atlas systems combine flood modeling, sea level rise projections and spatial zoning to guide development and protection decisions. In the United Kingdom, UK climate projections, known as UKCP18, are used in environmental impact assessment and infrastructure planning. France has applied heat island modeling to support urban greening and land use restrictions, especially in large metropolitan areas such as Paris. In Japan, multi-hazard platforms connect climate risks such as typhoons and heavy rainfall with broader emergency planning systems. Kenya offers an important example from a different context, where Copernicus-based climate risk profiles help guide agricultural planning and water infrastructure decisions. Together, these cases show that climate data becomes useful when it is embedded in planning systems, institutional routines, and clear implementation mechanisms. To integrate climate data into land use and infrastructure decisions, several groups of tools are required. The first group is technical tools, especially GIS platforms, downscaling methods, reanalysis datasets such as ERA5 and hazard simulation models. These tools make it possible to connect climate information with geography, topography, population, and infrastructure layers. The second group is analytical tools. Multi-criteria decision analysis helps compare land use alternatives, risk and vulnerability assessment supports composite risk scoring, and cost-benefit analysis can estimate the value of avoided losses from adaptation measures. The third group is institutional and operational tools. These include climate screening in planning and investment processes, DRR-oriented spatial plans, participation mechanisms, scenario stress testing, and adaptive planning cycles. In practice, climate data integration is never only a software issue. It depends on the interaction between data platforms, analytical methods, and decision processes. Effective planning emerges when these tools work together in a coherent governance framework. A strong decision-making system depends on access to reliable climate data from recognized sources. At the global level, the World Meteorological Organization supports coordination and standardization through climate service networks. The IPCC provides scenario families, such as SSP and RCP pathways, that underpin long-term climate projections and adaptation planning. Within Europe and beyond, Copernicus Climate Data Store offers open access to reanalysis products, projections, and impact indicators. NASA EOSDIS contributes satellite-derived information such as vegetation indices, soil moisture, and thermal anomalies, while NOAA Climate Data Online provides historical baselines that are useful for trend validation. Additional multi-risk datasets are available through UNDRR and UNEP platforms, where climate information is connected with socio-economic exposure. The importance of these sources lies not only in data availability, but also in credibility, comparability, and reproducibility. When decision-makers rely on verified and standardized sources, climate information becomes more defensible in policy, planning, and investment contexts. Climate data can be grouped into several types according to its planning function. Observed data includes measurements from ground stations, satellites, and reanalysis products. These datasets are essential for establishing baselines, validating models, and analyzing historical extremes. A second category is projection data, produced through global and regional climate models. These datasets help decision-makers examine future scenarios under different socio-economic and emission pathways. A third category is derived indicators, such as drought indices, flood recurrence models, and heatwave thresholds. These indicators translate raw climate variables into practical information that planners can interpret more easily. A fourth dimension is socio-economic coupling. Climate risk does not emerge from hazard alone. It also depends on exposure, vulnerability, and adaptive capacity. Climate data therefore needs to be combined with demographic, infrastructural, and economic layers. Different stages of planning require different forms of evidence, from baseline diagnosis to scenario assessment. For climate data to be genuinely usable, standards and interoperability are essential. Spatial and institutional harmonization cannot be achieved if datasets are stored in incompatible formats or described with incomplete metadata. In the European context, the INSPIRE directive plays a key role by promoting common rules for spatial data exchange. Fair data principles add another important layer by emphasizing that datasets should be findable, accessible, interoperable, and reusable. Standard file formats such as NetCDF, GRIB, and GOTIFF support model chain integration and allow data from different systems to be combined more efficiently. In addition, APIs from platforms such as Copernicus and NASA Earth Data enable automated workflows, dashboards, and dynamic analysis. Metadata is especially important because it ensures traceability and reproducibility, both of which are critical in evidence-based governance. Without shared standards, even high-quality climate data may remain difficult to apply. Interoperability therefore turns data availability into actual planning capacity. One of the most important uses of climate data is in strategic planning and territorial development. Long-term climate stressors such as rising temperatures, changing rainfall regimes and increasing flood frequency shape the spatial future of cities and regions. Climate data helps identify where these pressures are likely to intensify and where development should therefore be restricted, conditioned or redesigned. This includes defining no-build zones, adaptation zones and priority areas for green and blue infrastructure. Climate-informed spatial planning also supports urban microclimate analysis, which is increasingly important for heat-sensitive settlements. A well-known example is Copenhagen, where cloudburst modeling has been linked with urban design and zoning decisions to reduce flood risk while improving public space. The broader value of this approach is that spatial planning becomes more forward-looking and reduces risk before it is locked into the built environment. Climate data is equally important for infrastructure and investment planning. Infrastructure systems are long-term assets, and their performance depends on whether they are designed for future rather than past climatic conditions. Projected extremes in temperature, rainfall and wind can influence structural design, material selection, drainage capacity and system redundancy. This is why climate proofing has become a central concept in infrastructure governance. It means assessing vulnerability early and integrating resilience into design and financing decisions. Cost-benefit analysis is especially useful because it helps justify preventive investments by comparing adaptation costs with avoided losses over time. Major funding institutions increasingly require this kind of climate assessment. For example, federal projects in Canada use the Climate Lens system to evaluate resilience as part of investment approval. Climate data therefore turns infrastructure planning from a short-term engineering exercise into a long-term risk management strategy. Beyond long-term planning, climate data also supports crisis and prevention planning. In disaster risk reduction, one of its main advantages is the ability to model cascading and multi-hazard events. A severe storm may trigger flooding, which can then lead to landslides, transport disruption or infrastructure failure. By combining climate variables with topography, land cover and exposure data, planners and emergency agencies can prepare for these linked impacts more effectively. Climate data is also central to early warning systems, where forecasts are merged with local sensors and communication networks to support rapid operational decisions. Hazard, exposure and vulnerability maps guide evacuation planning, resource allocation and shelter management. Bangladesh offers a strong example, where flood forecasting systems using global models and local measurements have reduced mortality and economic losses. Climate data strengthens preparedness by translating forecasts into concrete actions that protect lives, assets, and critical services. Climate data becomes more effective when it is communicated clearly and open to participation. Risk information is often technically complex, so decision makers and communities need formats that are easier to interpret. Interactive maps, story maps, and risk dashboards help translate scientific data into actionable insights. These visual tools support scenario planning by allowing users to compare possible futures under different climate pathways and planning choices. Participation is equally important because local knowledge can complement formal data and improve legitimacy. Community-based disaster risk reduction shows that residents often hold valuable insights about recurring hazards, vulnerable groups, and coping strategies. When expert analysis is discussed together with local experience, decision-making becomes more realistic and more socially accepted. Climate data should therefore not be seen only as an expert resource. It is also a communication tool that can support dialogue, collective learning, and more democratic forms of resilience planning. Despite its value, climate data integration faces serious technical and data-related challenges. One major issue is resolution. Many global or regional models are too coarse for local planning, especially in dense urban areas or topographically complex regions. To become useful at municipal scale, they often require downscaling and bias correction, both of which demand expertise and computational resources. Another challenge is the scarcity of ground observations in many developing or rural contexts. Limited monitoring networks reduce calibration quality and increase uncertainty. Data interoperability is also a persistent problem. Inconsistent metadata, differing formats, and fragmented collection methods make it difficult to merge datasets across institutions. Finally, uncertainty itself is often misunderstood. Decision-makers may treat uncertainty as a reason to delay action, even though climate planning must work with a range of possible futures. The challenge is therefore not only generating better data, but making it usable in planning. Technical limitations are only part of the problem. Institutional, capacity and political challenges are often even more decisive. Responsibilities for climate governance are frequently fragmented across ministries and agencies, which creates overlaps, gaps, and inconsistent strategies. At municipal and regional levels, analytical capacity is often limited, so even where data exists, institutions may lack the staff or skills to interpret it. Funding is another barrier. Advanced modeling, monitoring, and digital infrastructure require long-term investment, yet public budgets are often constrained. Political time horizons also matter. Climate resilience usually requires action over decades, while many political systems operate within short election cycles. This weakens incentives for preventive investment. Low public awareness can also reduce pressure for data-informed decisions. These challenges show that effective climate data governance depends not only on information, but also on institutions, resources, and political commitment. To address these barriers, a clear implementation framework is necessary. The presentation proposes a four-step cycle that turns climate data into policy and planning action. The first step is data collection, validation, and standardization. Institutions need to identify relevant sources, check reliability, and organize data in a consistent form. The second step is modeling and analytical transformation, where raw data is converted into meaningful risk indicators through methods such as vulnerability analysis, flood modeling, or drought assessment. The third step is visualization and communication. Climate information must be translated into maps, dashboards, and scenario tools that non-technical actors can understand. The fourth step is integration into regulations, strategies, environmental assessments, and investment criteria. This is the point where data influences actual decisions. Importantly, the framework is cyclical rather than linear. It supports adaptive management, meaning that policies and plans can be revised as new evidence, new risks, and new priorities emerge over time. Successful implementation also depends on a clear distribution of institutional roles. At the global level, organizations such as the WMO, UNDRR, and IPCC provide standards, scientific guidance, and monitoring frameworks. At the regional level, platforms such as Copernicus and Climate Adapt help harmonize methodologies and support cross-border exchange. National governments play a bridging role by establishing climate services, embedding climate data into legal frameworks, and securing funding for implementation. Local governments are where operationalism actually occurs. Municipalities and regions use climate information in spatial plans, infrastructure projects, crisis planning, and public communication. They are also closest to communities and therefore central to participatory verification and local adaptation. The private sector adds further capacity through innovation, modeling tools, and infrastructure investment. This multi-level structure is important because climate risk governance cannot be managed by one institution alone. Effective implementation requires coordination across scales so that scientific information is translated into consistent yet context-sensitive action. When moving from general principles to practice, several implementation actions become especially important. A first priority is to create a unified climate data catalog with standard metadata so that institutions know what information exists and how it can be accessed. A second priority is to conduct risk and vulnerability assessments that combine hazard return periods, exposure layers, and vulnerability indicators. This creates a stronger basis for territorial comparison and priority setting. A third step is to use decision support methods such as multi-criteria decision analysis when planning infrastructure or evaluating land use alternatives. A fourth step is to introduce mandatory climate screening into environmental assessment procedures and major investment processes. This ensures that resilience is considered early rather than added later. Finally, monitoring tools are needed to evaluate outcomes through resilience indicators. These steps transform climate data from a passive repository into an active part of routine governance, planning, and investment practice. The integration of climate data offers clear benefits across public, economic, social, and environmental dimensions. For the public sector, it improves foresight, reduces uncertainty, and supports more transparent decision-making. Governments can justify planning choices more convincingly when they are based on verifiable evidence. Economically, climate-informed decisions reduce disaster losses, improve investment stability, and align with emerging ESG and green finance expectations. For society, the benefits include safer communities, better preparedness, and stronger adaptive capacity. Citizens gain access to clearer information, and this can support more meaningful engagement in planning processes. Environmental benefits are also substantial. Climate data helps guide the protection of ecosystems, water systems, and green infrastructure that contribute to resilience. Perhaps the most important long-term benefit is the shift in governance logic from response and recovery toward risk management across the whole lifecycle of development. At a broader strategic level, climate data should be understood as a global public good. Climate risks do not stop at administrative borders, and many challenges such as floods, droughts, and heat stress have regional or transnational dimensions. Shared data standards and open access therefore strengthen cross-border cooperation in both climate adaptation and disaster risk reduction. Climate data integration also supports compliance with major international agendas, including 11 Sudanese pounds on sustainable cities, 13 Sudanese pounds on climate action, the Paris Agreement, and the Sendai Framework. In addition, more stable and predictable planning environments can improve national competitiveness by reducing systemic vulnerability and investor uncertainty. When decisions are informed by transparent evidence, public institutions can act more consistently and accountably. Climate data is therefore not only a technical input. It is part of a wider transformation toward resilient governance, international solidarity, and evidence-based development. In conclusion, climate data has become essential for operationalizing disaster risk reduction across planning, investment, and governance cycles. This presentation has shown that a structured framework can bridge science, policy, and practice by connecting data sources, analytical tools, institutional roles, and implementation steps. Resilient development depends not only on having data available, but on integrating it continuously into decision-making and building the capacity to interpret it responsibly. When climate information is used well, it can reduce losses, save lives, and support more sustainable patterns of development. At the same time, the effectiveness of this approach still depends on political will, institutional coherence, and public engagement. Data alone is not enough, it must be embedded in a culture of evidence-based governance. A future protected by data is possible only if climate information is treated as a practical foundation for prevention, adaptation, and long-term resilience.